Hello, my name is Professor Daniel Stewart, and today I will be covering significant figures, rules for multiplication and division. In a separate presentation, I will cover the rules for addition and subtraction. Why are significant figures a thing? Well, when data is obtained from an instrument, there is always a small degree of uncertainty associated with that measurement. There is no device capable of zero uncertainty. When we use this data in calculations, we want to make sure that this uncertainty is retained in the answer, so we know how much our results can be trusted. When we look at values associated with measurements, it's important to know what numbers are considered significant. Non-zero values are easy because any non-zero value is considered significant. So if you look at these examples here, all the values that are not zero are highlighted and they are significant. The zeros, in this specific case, are not. The following examples will deal just with zeros because determining if they are significant or not is a little trickier. Any zeros between two other significant digits are also significant. You know that the 1 and the 9 are significant from the last rule, so the zeros in between those two significant digits are also significant. The 0 here is significant because it's between two non-zero numbers, where these zeros are not, and therefore are not considered significant figures. The same rules apply on the following numbers. Trailing zeros that are to the right of the decimal place are considered significant. As you can see here, the zeros that are to the front, the leading zeros, are not significant, but the zeros to the right of the decimal place that are trailing are. That's the difference between, say, 3,500, where the decimal place would be inferred to be right here. These zeros are not significant, where something like this, the zeros are significant because they are trailing and to the right of the decimal place. The leading zeros in these examples that are to the left of the first significant figures are considered placeholders. Multiplication operations with significant figures. Let's assume that we measured these dimensions, length, width, and height. If we were to compute volume using these data, we would say volume is equal to the length times the width times the height. We would substitute these values for the respective variables, write our equation, and solve using a calculator. The calculator would read 11.25. However, we want to round this answer to 3 sigfigs, because our original measurements had 3 sigfigs. Therefore, we answer that the volume is equal to 11.3 cubic centimeters. These cubic units on centimeters are the result of centimeters times centimeters times centimeters equaling centimeters cubed. So here are the key points. The length, the width, and the height each consist of 3 significant figures. When we perform the multiplication operation, we must produce an answer that is rounded off properly. The answer must consist of the same number of sigfigs as the data, which in this case is 3 significant figures. Let's look at another example. In this particular example, the height was only recorded to 2 significant figures, while the other 2 dimensions have been recorded to 3 significant figures. This could be perhaps that the person who measured the height might have used a ruler like this that doesn't have as much resolution. You cannot be as precise with this ruler as you could with this. That might be the reason, or perhaps they just got lazy. However, when we go to compute the volume and multiply length times width times height, the first 2 values have 3 significant figures, the third value only has 2, but our calculator would read 11.5. However, we would need to round this answer to 2 sig figs because one of our original data was recorded with less certainty. The answer that we would record should be that the volume is 12 cubic centimeters. The key points are that the data with the fewest number of significant figures constrains the number of sig figs in the answer. And in this example, the length and the width have 3 sig figs, but the height only has 2 sig figs. Therefore, our answer can only have 2 sig figs. So we round our answer off to that same number of sig figs as you see here. And in this example, we present 12 cubic centimeters as our result. That's important because the person who is reviewing our calculations could immediately infer that we used an instrument with certainty to only 2 sig figs, just by looking at our calculation. Division operations. In terms of rounding off your final answer, division operations work much the same way as multiplication. The data with the fewest number of significant figures constrains the number of significant figures in our answer. Here's an example. Find the density of a material with the following properties. Notice the mass has 3 significant figures, as does the volume. The density, being the mass divided by the volume, would be computed by dividing 14.2 by 3.35. Our calculator would display the answer like this. However, this is far too many significant figures to record. The data only have 3 significant figures, so that's the same number of significant figures our calculated answer must have too. Our final answer that we record would be 4.24 grams per cubic centimeter, 3 sig figs, because our data only has 3 sig figs. Here is another example. Find the density of a material with these following properties. The mass, notice, has 5 significant figures. The volume, 4 significant figures. When we compute the density, we're dividing a 5 significant digit number by a 4 significant digit number. The calculator will display this and more as an answer, and we know that we need to round this off. We're going to round to 4 sig figs, or significant digits, or significant figures, because between our 2 bits of data, this one had 5 sig figs, this one had 4 sig figs. The one with the fewest number of sig figs constrains our answer to being 4 sig figs. We record 9.608 grams per cubic centimeter as our final answer. Thank you for watching.